Hey, this is Group 9, and today we're going to give a short presentation about a robotic arm. Our team has spent the last 3 months developing a robotic arm. We started with a very broad range of ideas, from the very complex down to the very simple. It should be noted that one of our team members, the project leader Rigo, had actually been working on this as a personal project since about the middle of the year, and so we had a lot of different ideas to work with and play around with, but overall we had a pretty strong idea of what we were going to work with. Now, in terms of what we're doing, we're basically creating a sort of educational service product which can be used by people to practice developing robotic arms themselves. In so doing, we're going to have a few competitors such as Lego, books, online education, and just regular DIY projects that other people use. But we do feel we can fulfill a specific niche in the market. I'm sure there are educators and also people that want to learn for themselves that would like a more practical, guided approach with a strong basis in engineering, and that is what we're trying to provide here. So essentially what we're doing here is the idea for the project at its bare bones was a robotic arm. However, in terms of how we would implement it as a mechanical engineering project, we decided to create a service where we could train other people to use robotic arms and to build robotic arms from scratch using 3D printing. So the idea combines a service model with robotic arms, basically. Now we, like I mentioned before, had a lot of different ideas which we played around with. We had to create criteria to make these ideas valid and useful. In terms of the criteria, we delimited the criteria into two different categories, that being hard and soft criteria. The hard criteria was absolutely necessary for the project to function and to reach completion, whereas the soft criteria were just a group of things that would be nice, but not necessarily absolutely important for the project to be completed. Further, we weighted the criteria on a scale from 1 to 5, 1 being the least important and 5 being the most important. Looking at this chart, you can see here that because this project itself is completed by 3D printing, and so dimensioning was the most important criteria, a form of hard criteria that had the most important weighting on it. But also the stiffness of the plastic material used in the 3D printing, as well as the geometry, though that was considered to be more of a soft criteria, but it relates to the dimensioning. Anyways, in any case, we had different criteria. We delimited it between hard and soft criteria and weighted it from 1 to 5. Now, when we created this different criteria model, we then moved to coming up with a bunch of different ideas and designs. We came up with 10 different concepts in total. You can see some of the more critical ones here that we played with. One being concept one, that is, being the model that we ended up going with effectively, but model 1 was intended to be printing efficient. That means it was supposed to be quite easy to print. We were thinking of the end user here. Model 3 was meant to have a very low center of gravity, so that it would be very stable, very sturdy, very strong. Model 4, or concept 4, sorry, was intended to be the opposite of the other concepts in that most of our concepts were based on a robotic arm with its base perpendicular to the ground. We decided to create a robotic arm that could have its base on a ceiling or maybe on a wall mount, so we tried to create a slightly different way of positioning the robotic arm. In Model 8, we had this crazy idea of making a robotic arm with multiple arms. This would be way too complicated to complete in this project, but it was just an idea. Anyways, we basically played with all these different concepts. We evaluated them based on the hard and soft criteria, and eventually we narrowed the project down to concept 1. We did encounter a number of different problems, and in encountering those problems, we had to come up with different solutions to deal with those problems. Some problems that we had to deal with were things like cost, printing time, disposability, and user experience. Our goals were to optimize each of these metrics. First, we wanted to reduce the cost as much as possible to make a low barrier for entry for any customers, potential customers. Additionally, we needed to make sure that the 3D printing time was as short as possible, considering most of our clientele base was going to be amateurs and do-it-yourself enthusiasts. We needed this to be something that they could do over the course of, a weekend or a Friday night, not something that was going to take, days and weeks to execute on. Additionally, we had concerns about disposability, both for the parts and the overall model once done, so we tried our best to optimize the disposability in terms of materials of the robotic arm. And finally, we wanted to make sure that we could create the best possible user experience for our customers. This was again aimed at mainly amateurs, so we wanted this to be something that they could get into quite easily, learn something about robotic arms and 3D printing, and come away from it better than when they started. As such, there were a few compromises that we needed to make. We couldn't make things as complicated as they could be. This ideally was meant to be an introductory robot for users to engage with, and as such, we couldn't create too much complexity in the design. Also, the wiring and programming for the robotic arm had to be as accessible as possible for a beginner. Now, there's always a temptation in engineering to over-engineer things to make it as close to perfect as you can possibly make it. The problem is that this can take way too much time. So in engineering, you need to learn to balance the art of doing what you have in mind and creating everything you possibly could with what actually is possible, especially given the resources you have available, such as time. So now to discuss more about some of the challenges that we faced and that I briefly introduced before, Rigo, the project leader, is going to discuss in depth what challenges we faced and how we overcame them, and also give more of an idea of how the project moved forward and where it was in its end state.
So to talk about the problems we have to solve briefly, because there were many problems and not all of them are here, but these are the key points in terms of adding as much stiffening as possible, adding accessibility, it being easy to assemble by any person, so any skill level. So firstly we have stiffening, of course. This was added just using Engineering Sense. We didn't really do any FME simulation for this, even though technically you should. Fastening was a major issue. At first we had some slot fits which seemed too fiddly and liable to fatigue, so we replaced these with snap fits. In this slide you can see the female side of the snap fits. Thirdly I would say, accessibility. All the motors should be easily installable but also still accessible for wiring, though of course the order which you would wire or install them might vary between users, or well, frankly we haven't decided this yet because that would be under assembly and that report is still undone. Fourthly, we have electronics. Pretty much straightforward. You can either print it in one piece as it is seen here, you can print them in separate pieces and glue them on, but the main point again is accessibility. So it's easier to wire and of course wire routing itself, but again that would be done in manufacturing and then the report is still undone. And then the final form, well, kinda. We had some other ideas. We wanted to do fully 3D printable fasteners instead of normal nuts and bolts. This was of course a bit too difficult and time consuming, so that idea was scrapped. We wanted to add wiring, but there was a problem in visibility, so it's not present here. Plus we don't really have access to certain software, and the roundabout ways to fix this are difficult, or again time consuming. And we wanted to do a modular 6-axis, but again too time consuming.
Okay, to conclude, we learned a lot from this project. Most importantly, we learned how to be more efficient in dividing up the tasks of a project and doing what's important first, focusing on calculations and modeling, finite element modeling. Additionally, if we could change some things, we would have spent more time in the iterative process at the beginning, design and analysis, rinse, repeat, and it may have helped to have some more people on the team and rethinking some things and resting on things more. Anyways, thank you very much for watching and enjoy the rest of your day.